12.4 is looking at limits at infinity. Just as a side note, that would be like the limit as x approaches infinity or negative infinity. We're not looking at, well, the limit looks like it goes to infinity, so that does not exist. We're looking at as we look all the way to the right of our graph, or higher and higher numbers for x values, or to the left with our lower and lower numbers. So for each of these on your sheet, you are going to want to fill in your table. So like if I did 1 over 0, that would be undefined, and I'll write undefined there. 1 over negative 1 would be negative 1. 1 over 5, negative 5 would be a negative 1/5. I will say go ahead and make these decimals for all of these tables. It'll make it a little bit easier for you to see these. You are going to fill in your table, and you are going to sketch a graph and you can graph these on your calculator, but of what this looks like. So take a minute, finish filling in your table, and sketching your graph. So pause this while you do that. All right, for negative 10, you should have gotten negative 0.1. Negative 50 should be negative 0.02. Negative 100 should be negative 0.01, and negative 1000 should have been negative 0.001. As I look at this, each number is getting closer and closer. I mean, I'm getting more and more zeros here, closer and closer to 0. So according to my table, or numerically, it looks like my limit is going to be 0. I'm going to check that with my graph. So I'm going to sketch my graph, which is not awesome, but it is a sketch. Oops. Ignore this piece here. And I'm looking as x approaches negative infinity. So that would be as I'm going this way towards the left, my graph should be getting closer and closer to 0. So my graph makes it look like it is 0 as well. So my limit is 0. I want you to pause this. This will take you about 10 minutes, but fill in your table and your graph for all of these. I will then go through them with you and talk about some of your rules. I'm being serious. Pause this and do that. All right, a few rules to look at. If you look at this one, we have this fun rule for limits that says if r is a positive real number, then the limit as x approaches infinity of 1 over x to the r, so x to the first, second, third, any positive number there that's real, is going to be 0. This same is true if you do your limit as x approaches negative infinity. So basically, anytime I have 1 over x, whatever the exponent is, it's simplified, so not negative, all that, it's in that denominator, then I'm going to have 0 as my limit. On this one, check your table with mine and check your graph with mine. Looking at my table, 3.25, 3.67, 3.97, 3.9988, 3.9997. This is getting closer and closer to 4. Looking at my graph, I am going to infinity, so I'm looking to the right of my graph, and that y value is approaching 4. So according to my graph, it's 4. To do it algebraically, the only rule you know for your limits as they go to infinity is that if you have like 1 over x squared, or 1 over x to the third, or 1 over x, that part is 0. So what you're going to do is use some of your properties from earlier in this chapter and split this to be the limit as x approaches infinity of 4 minus the limit as x approaches infinity of 3 over x squared. I know that the limit of a number, no matter what x is approaching, is always going to be that number. So that's 4 minus. And we already said that 1 over x would be 0 if I'm going to infinity. The same is true for 3 over, 5 over, 100 over, because I'm dividing that top number by infinitely larger numbers. So I should be getting closer and closer to 0. So this limit is 0. 4 minus 0 is 4. So my limit, whether I look at it numerically, graphically, or algebraically, is 4. Okay, on number 3, yeah, my table starts up kind of high and then it goes down negative, and then it's looks like it's getting closer and closer to 0. I don't care what it's doing right at the beginning. I'm looking as I go to infinity. So as my numbers get larger, it does seem to be getting back closer and closer to 0. Same on my graph. Yeah, it went up and then down, but it does start leveling back out around that 0 there. So according to my table or my graph, my limit's going to be 0. But again, you are going to be asked to do this algebraically, so you need to be able to do that. On the previous slide, we were able to just split this to the 4 minus with something over an x, because we had a rule for that. We aren't going to be able to split this. So what you are going to do is divide each term in the numerator and denominator by the highest powered x in the denominator. So again, you're dividing every term, numerator and denominator, by the highest powered x in the denominator. So when I look at my function here, my highest powered x is that x squared. So I'm going to divide everything by that. So the limit as x approaches infinity, and I'm going to have negative 2x over x squared plus 3 over x squared over 3x squared over x squared plus 1 over x squared, which if I simplify that, that's going to be the limit as x approaches infinity. Negative 2x over x squared, one of your x's would cancel, so that would simplify to negative 2 over x. 3 over x squared does not simplify, so I'm going to just leave that as 3 over x squared. 3x squared over x squared, your x squareds would cancel, so that'd be 3. And 1 over x squared does not simplify. At that point, you can actually evaluate your limit, just like we did on that previous slide. So if I'm doing my limit to infinity of any number over an x, as long as that exponent for that x is positive and real, you're good. That limit is 0. Same here, 3 over x squared. That limit as x approaches infinity is 0. My limit of 3 is 3. And my limit of 1 over x squared is 0. So here I have 0 over 3, which is 0. So my limit as x approaches infinity of negative 2x plus 3 over 3x squared plus 1 is 0. On number 4, looking at my table, it's kind of hard to say. It's not going to 0. I'm noticing a lot of 6's here. And if you remember that 0.66666 is 2/3. Now, this was negative, so it's a negative 2/3. And it's hard to tell exactly on your graph, which is why that's not great either. But, I mean, it almost looks like it's 1, except for that if you really zoomed in or checked your table closely, it never really goes past that 0.666666. So that's what it is approaching. Doing this algebraically, you're going to do the same thing you did on the previous one. So my highest powered term in that denominator is x squared. So you're going to divide everything by that. I want you to pause this and try it on your own. Simply copying it as I do it or going back and just copying it without trying it on your own does not teach you anything. I'm being serious. Pause this. So here's my setup where I've divided every term by x squared. That next step, you should simplify those. So here I've simplified each of those. Now I'm actually doing my limit. My limit of -2 is -2. My limit, as I'm going to infinity, of 3 over x squared is 0. In the denominator, my limit of 3 is 3. My limit as I go to infinity of 1 over x squared is 0. That reduces to -2/3. What's nice about doing it algebraically, besides the fact that you need to know that because I will ask you to do them algebraically, is you don't have to guess by your table what it looks like it's going to be or guess by your graph what it looks like it is. It tells you exactly what it is. So my limit is -2/3. I want you to try this one on your own, algebraically. Then we'll look at what's really happening on the graph. Here's my setup. This is one of the most crucial parts of this section, is being able to do the algebra. So without these in your notes, you will not get credit for your notes. From there, you should be simplifying each of these. Then I'm doing my limit. Now, I'm going to skip that -2x for just a second because I know that 3 over x squared is 0, 1 over x squared is 0 for those limits. The limit of 3 is 3. But here, this -2x, if I tried to plug infinity into that, I'm going to have -2 times an infinitely large number, which is just going to keep getting me closer and closer to negative infinity. So that would give me -infinity over 3, which would still be negative infinity, which means my limit doesn't exist. So according to this, my limit doesn't exist. Let's check our table and our graph. Looking at my table, these numbers are just getting bigger, like they don't seem to be leveling out, and they're negative, but they're just getting bigger and bigger and bigger in the negative direction. So you get negative infinity there, which means does not exist. Looking at my graph as I go to the right, my graph is going down, down, down. It never levels off, so it's going to negative infinity, which means my limit does not exist. So up here, my limit does not exist. Sometimes you'll be asked to do a graph, sometimes you'll be asked to do it numerically or with a table, and sometimes you'll be asked to do all of the algebra. Now, what makes it nice is there's actually a rule to follow for each of these, that you can check your answer in like a half a second. So, very bottom, when the degree of the numerator is less than the degree of the denominator, so if you look back at your problems, that should be like number 3. So the degree of the numerator, which would be a 1, is less than the degree of the denominator. Here I got my limit to be 0. That is always going to be the case. So that makes me think of back when we did our asymptotes. If the degree is bigger on bottom, we say, yo, what's up? Because back then that would be y equals 0 for that horizontal asymptote. Now we just kind of pulled a 0 out. But I still remember yo, Bob, bigger on bottom. When the degree of the numerator and denominator are equal, this is going to be like number 4. So if I notice both my degree of my numerator and denominator are both x squared, but you're always going to have that highest power. And if you look at these two terms, your limit was actually just the coefficients out front, that -2/3. So the ratio of the coefficients of the highest powered terms. As long as they are equal, all I care about is the coefficients. When the degree of the numerator is greater, so when it's bigger on top, that should be like number 5, because it was an x cubed over an x squared. Here your limit did not exist. That will always be true. So my limit does not exist. And that's going to be like no bot. So you can use these 3 here to quickly check. But remember, a lot of the time I will require the work, so the graph, the table, or the algebra. Pack out.